Hello viewer, welcome to this session. In this session, we are going to talk about how to find the degree of freedom of a rigid link or a system of link. We also say the bars in two-dimensional space particularly. So in this session, first we will understand what is degree of freedom, and then we will also see that if we are putting some constraints on these links, how the degree of freedom will change. For example, if I am going to put a pin joint or I am going to put a roller joint, how the degree of freedom will change. And finally, we will take this example where we are having a system of links. Here we are having four link, and the fifth link will be the fixed part. And if we are interested to find the degree of freedom, how we can visualize. I know that you are having a formula which is there in the theory of machine course. There the direct formula can be applied to get the degree of freedom, but the objective of this session is to make you understand. You will be able to visualize the degree of freedom of the system. So let's start with the definition of degree of freedom. Degree of freedom is generally defined as the number of independent coordinates required to define the position of a point or a body. For example, if I am having a point in 2D space, for example, this is XY plane and I am having a point here. So to define the position of this point, I need these two distance or coordinates. Let's X and Y are the coordinate of this point. So X and Y are actually degree of freedom which is required to define the position. Or suppose the point is moving in the space, and for a given instant of time I want to define the position. Here also again I need X and Y. That means a point in the two-dimensional space will have 2 degree of freedom. Instead of point, if we are having a body, in case of body an additional degree will be added. And how? Because if the body is there in the two-dimensional space, please understand, here we are only talking of the two-dimensional space. There will not be any translatory motion across the plane. That means it's a 2D. So in the case of 2D, the body can exhibit X and Y translatory motion, but in addition to the translatory motion, we are also able to visualize the rotation of the body about this third axis. So we can say the theta about the Z axis. All the three motions are only in this 2D plane. Even though the rotation is about the Z axis, but the rotation plane of the rotation is also this considered two-dimensional plane. So in case of a body in the 2D space, the total degree of freedom will be 3, not the 2. But in case of point, because for the point we cannot say any rotation, so the degree of freedom will be 2. The second definition is the total independent motion exhibits. So that is also fairly clear by the second example. Now here you see I am emphasizing this independent term. Difference between dependent and the independent coordinate. To understand this philosophy, let's take an example of a pendulum. Suppose I am having a pendulum and the length of the string is L. The pendulum is, let's, oscillating, and for a given instant of time the position of the pendulum is here. If I am interested to find the position of this pendulum at this given instant of time, let's first consider that this is my origin and this is X and Y. So for this given instant of time, let's, this height is defined by Y and this distance is defined by X. So do you think that this pendulum is also having 2 degree of freedom, because I need two coordinates to define the position? And please ignore the rotation because it's a spherical body, so or it's a point mass, so there will not be any rotational degree of freedom, only two translational degree of freedom I can consider. So first hand I can say that there are 2 degree of freedom, but let me tell you, it is not having 2 degree of freedom, it is having only 1 degree of freedom. Now why 1 degree of freedom? As I said that it should be independent. In the given case, if you know the X value, you will be able to get the Y value because these two coordinates are connected to each other. How? Let the length of the bar here also L. If I will complete this triangle and I know the X value, if I know the X value, this is my L length. So the length or the Y coordinate can be defined by the total length minus this length. And this is how much? This is L square minus X square under root. So X coordinate is X and the Y coordinate will be what? Y coordinate will be L minus under root L minus X square. So once you know the X value, you will be able to get the Y value. So Y is not independent, it is dependent. Similarly, if you know the Y value, then you know the this remaining length, and using the same Pythagoras theorem you will be able to get the x value. So if you know the x, you will be able to get y. In addition to that, another coordinate that can be used to define the position is the theta. And theta, x and y, all three are dependent to each other. If you know the x, you will be able to get y, and also you will be able to get the theta, because you know the length of this entire right angle triangle. If you know the y value, you will be able to get x and theta, or if you know the theta value, you will be able to get the x and y. So ultimately there is only one coordinate which is independent, therefore the degree of freedom of this pendulum, which is a simple pendulum and can move only in this two-dimensional plane, is on 1. So I hope now you are having understanding of degree of freedom, and let's come back to our rigid body bar and to find the degree of freedom of this bar. So as I said previously that for a rigid body in the space, total degree of freedom will be 3. Please, again I am saying that in 2D space. So for this free link which is having free end, total degree of freedom will be 3. But if I am going to add a pin joint here, so let's add a pin joint here and now try to understand now how many degree of freedom left. So first we must understand how the pin joint work. Pin joint is actually nothing but, if we are having two brackets, there is a hole. If I will put this link here and then there is a bar. So because of this constraint, now the link is not able to move anywhere. It cannot go away in the x direction as well as it cannot go in the y direction, but it is able to rotate about this axis of rotation. That means now x has gone, y has gone, but the theta z is still alive. That means the pin joint bar with the pin joint is having only 1 degree of freedom, and that is what? That is the rotation. So we can say that when we are adding a pin joint, earlier the total degree of freedom was 3, and then there is a restriction of 2 degree of freedom x and y, so we are having only 1 degree of freedom left. That means a pin joint put a constraint on 2 degree of freedom. Please remember, this is very important concept. Pin joint will put a constraint on 2 degree of freedom. The third is the roller joint. In case of roller joint, it is similar to the pin joint, but in addition to one rotational degree of freedom, it is also having free about one translatory motion. I can make another diagram. Suppose we are having a bar here. This is a roller, and the roller can slide in this channel. That means what? This bar is able to rotate about this point as well as it is able to move in this direction. That means theta z is alive, x is alive, but y is not there. That means the total degree of freedom with a roller joint will be one rotation and one translatory motion. So earlier I was having three uh, degree of freedom if it is free. When I am adding a roller joint, I am putting a constraint on 1 degree of freedom, remains will be 2. So in case of a roller joint, there will be a constraint on 1 degree of freedom. In case of a pin joint, there will be a constraint of 2 degree of freedom. Please remember this concept. These concepts are really important, and you may get some objective or multiple choice questions based on this philosophy. Now the last part of this session, we want to understand total degree of freedom of this 5 bar or 5 link mechanism, where one link is this fixed joint and remaining 1, 2, 3 and 4 link. But for this we must understand another important concept, that if we are having two links connected, what would be the degree of freedom. And to understand this, let's consider first a single link which is free in the space. And I know if the link is free in the space, there will be 3 degree of freedom. Another link which is also free in the space, it is also having 3 degree of freedom. But if I am going to connect these two links, still I am not putting any constraint as a fixed joint or the pin joint with respect to the ground. I am now having a pin joint here. These two links are now connected. So what do you think now, whether we are having 6 degree of freedom or no? No, there will not be 6 degree of freedom. Why? Because now the second link is only having one rotational degree of freedom free, because the position of any point of the link is just defined by the theta, but the first link is still having 3 degree of freedom. So ultimately, if I know the position of this end and I know the length of the bar, I only need the theta value to define the position of any point of this bar. That means for the second bar, now I don't need x and y. For the first bar, I need all x, y and theta. So ultimately, when I am having two links connected, but the entire system is still free to move in the space, the total degree of freedom will be 3 plus 1, total 4 degree of freedom. So let's try to understand the entire system now. This is link 1. So I would say that first link is this, that means it is having 3 degree of freedom. Now the second link, it is having 1 degree of freedom. This is third link, it is also having 1 degree of freedom, and the fourth link, it is also having 1 degree of freedom, because every time when you are having a pin joint for a given link, it is going to constrain 2 degree of freedom. Earlier it was having 3 degree, but as I am putting a pin joint, the degree of freedom will be reduced by 2, and I am having only 1 degree of freedom, that is rotation. So total degree of freedom for this fourth link connected with a pin joint will be 1 2 3 and 3 6 degree of freedom. As soon as you are going to put a pin joint here, that means for the entire system you are going to put constraint on 2 degree of freedom. So the total degree of freedom remains will be 6 minus 2 will be 4 degree of freedom. If I am going to put another pin joint here, again I am going to restrain 2 degree of freedom. So 4 minus 2, that means remaining degree of freedom will be 2 degree of freedom. So this system which is having 4 link connected with the 2 pin joint will have 2 degree of freedom. So this is what about the degree of freedom. But if you want to visualize how these degree of freedoms are 2, if suppose I am giving a clockwise rotation to this system, you will not be able to predict the rotation of the last link. It may go in the clockwise direction or it may go in the counterclockwise direction depending on the rotation of these two links. But if you will try to visualize a simple 4-bar chain mechanism, there you are having only 4 link, and here also you can calculate. Earlier when there were no two joints, we can say that 3 plus 1 plus 1 total 5 degree of freedom, and as soon as I will put two pin joint on these two positions, there will be restriction on the 4, and the remaining degree of freedom will be 1. That means if I am giving a clockwise rotation to this link, I will be able to predict the rotation of entire system. But in case of another link which is here, I will not be able to predict the rotation of the last link. Even though I am giving a clockwise rotation to this, based on the length of the link, the rotation may be clockwise or counterclockwise. That means the system is having two independent motion, and because of that we consider 2 degree of freedom. So I hope with this small example you will be having a flavor how to visualize the degree of freedom of a link or a system of link. In the next session, we will further discuss the degree of freedom concept for a different type of system where we are having pulley and masses, and we will understand the concept more thoroughly. So I'm closing this session. Thank you.